Alright, this is a quick Ansys Mechanical tutorial about a relatively simple but also pretty interesting problem. Okay, so the problem here is this. If you have a living hinge model like this, where we need to model the placement of the cap onto the top of this other piece through, as you can imagine, taking this piece in your hand, right, rotate it over until this thing right here, right, clicks onto the arm, right? Let's say that's the problem statement. So how do you model something like this? Because if you think about it, it's not really just a rotation, right? Because you have to lift this piece up a little bit and move it a little bit towards the left. I have a pretty simple rotation here, but how do you model something like this? Because you can't exactly do it around the center here. Like, where do you find the rotational axis? And that is the nature of the problem statement, right? I find this problem really interesting when I first encountered this, and I wanted to share this. So the way you think about this kind of model, right, really, it's really not just a simulation problem, right? A lot of this is really about understanding the geometry of the problem that you're trying to model, right? So the way I think about this is that if you can think about a block, right, a rectangle here, right? Imagine this is the piece that represents this piece right here, right? Let me take this all the way to the left, right? You can imagine this piece right here represent the left side of the block, and then on the other side represents the cap, which is going to be rotating over until it hits the top of it, right? So the question here is, if these two blocks are mirrored across this axis right here, this little line right here represents the mirror between these two sides, right? How do I make sure when I rotate this thing over, it's going to go sit on top of it, also slightly translated? Because if you can think about this, right, this piece right here has to be slightly translated in order to click onto the arm. So that's the way we're thinking about it. So how do you create a rotation such that the rotation will force this piece to be ending up above it and also a little bit slanted, a little bit sort of shifted towards the left hand side, right? So it turns out the way you can do this, right, is to actually define a arbitrary rotational axis, which is represented by the axis of this circle right here, right? And the distance between this axis here relative to the center plane, right, which is about 0.4 in this case, represents how much x direction or z direction shift you have relative to this block. And then the vertical shift, which is the center axis of here relative to the top surface here, that center axis shift is going to represent how much this thing is shifting upwards. So to demonstrate this, okay, to demonstrate this, the way we can do this here is that I can create another mirror plane here and another mirror plane here. So I'm going to demonstrate this right here. So in the second sketch, what I did here is I created a center axis here, which is going to mirror this cap part to the left hand side, right? As you can see, this thing is now shifted by about 2 times the distance between here to here, right? So if you look at my first sketch, right, the distance here is 0.4. The shift over is going to be 0.8 because it's going to be 2x that distance, and that's how much we're shifting this piece over. And then on the other hand, this axis right here is going to shift this upward, right, by 2 times the different distance between here to here. So if you remember from the previous sketch, right, previous master sketch, this 0.4 right here represents half of how much the cap is going to shift upwards when it gets rotated relative to this rotational axis, right? So now with this understanding, the end result here is this, right? So end result is essentially look like, as you can see, this nodal point is going to come to that nodal point, right? Because as you rotate this point will become that point. And as you rotate this point will become that point. And you can see these two circles are concentric, which means that is my rotational axis, which is going to shift this block upwards by 2x the distance here, and it's going to shift to the left hand side by 2x the distance from here to here, which is a gap between here to here, right? So the way I define the rotational axis, right, is based on this master sketch here, where this is how much the block is going to shift towards the left hand side. 2 times this is going to define how much the block is going to shift upward. And this right here is going to define my rotational axis. So the way this model is built is exceedingly simple. As you can see, if you can understand what I just illustrated here, sort of, geometrically, right? All I have to do to generate the rotational axis, right, is to create a dummy feature that look like this. You see, this right here is going to serve as the basis for my revolute joint, right? So this is a baggy to baggy revolute joint. This is going to be reference, and these nodes right here is going to be the mobile side, right? These nodes right here. So these nodes are going to rotate relative to this axis, which is defined by the reference axis here, along the z-axis, right? And as you can see, I have a joint rotation here, which is going to rotate this by this much. This is in radian. Let's just change this to degree to make it easier for people to see. You're going to rotate by 180 degree, which means when this thing rotates by 180 degree, it's going to end up certain distance towards the left hand side and certain distance above the top of the cap, which represents essentially the motion of you placing the cap over, right? Rest of the constraints is pretty easy to understand, so I don't even need to go over them, right? So as you can see, as I rotate this relative to this rotational axis, the cap is going to end up slightly to the left hand side and slightly above the cap, creating that essentially motion where this thing is going to sit on top of the arm. And that's how you do a what seems to be a difficult to define motion, but all you have to do is to use geometry, right, to find the rotation axis that's going to give you what you want. This is why I also say, right, having the right CAD skill is critical for simulation, because a lot of the simulation problem and the boundary condition definitions are geometric definitions.